Morning everyone, welcome back. So this is another data analysis video, still on the topic of the binomial distribution. So this is another video in a kind of a series looking at probability distributions and models. And if you've seen the previous video, you'll know what I did in that video is I demonstrated how to manually calculate the probability mass function and the cumulative distribution function for a binomial distribution. So in order to do that, what we did was we created a function that would allow us to work out the factorial of a number. We used that to create a function allowing us to work out the binomial coefficient. Then we used that function in another function that we created to create the binomial probability mass function, and then we used the probability mass function in another function to obtain the cumulative distribution function for a random variable that follows a binomial distribution. So that was the hard way to do everything. In this video, what I'm going to do is demonstrate a similar sort of thing. I'll use the same examples essentially, but using the math library from Python. And in the next video, I'll kind of demonstrate similar stuff using SciPy. So much easier to use SciPy and existing software libraries. The purpose of the previous video and kind of this one a little bit as well is to develop a little bit of intuition, a bit of understanding around the binomial distribution. So as a quick recap, the binomial distribution, this is the binomial kind of probability model, can be used to model real world scenarios where events can be classified as one of two possible outcomes. So they could be a success or a failure. And using the binomial, we can calculate the probability of obtaining a given number of successes, say x or k, from a fixed number of trials n, with a probability p of success on each trial that does not change. And also, there was if you remember, there's a fourth condition that was the outcome of each trial is independent of all previous trials. Okay, so what I'll do in this video is use the binomial to calculate some probabilities. So specifically, we use the math library to work out the probability mass function for the binomial and the cumulative distribution function to obtain some probabilities. Okay, so to start with, what I'm going to do is import math. So I'm going to import the math software library from Python. Didn't do that last time. We kind of just coded the functions ourselves, and in this occasion the math library doesn't have a function for the binomial distribution directly, but it contains some useful functions that are kind of needed to calculate the binomial. It contains a function called comb, C-O-M-B, which I think will be short for combinatorial, which gives us the binomial coefficient, so to speak. So n choose k. If you remember, we calculated that manually in the previous video, and it kind of allows us to work out using the factorial of a number from n trials how many k number of successes we are observing. Okay. So this makes life a lot easier than where we did this manually in the previous video, as it allows us to use the comb function when defining a function that calculates the probability mass function for the binomial. So the first thing we're going to do really is define a function for the binomial PMF, the probability mass function, and we're going to make use of this comb method, this comb function from math. So if you recall from the previous video, I defined a function called binomial PMF, probability mass function. So it's a discrete, obviously a binomial distribution takes on discrete values. So we're going to use the def reserved word keyword. Binomial underscore PMF is the name we're going to give the function we're creating, and it's going to take three arguments, n, x, and p. So number of trials, number of successes, probability, fixed probability of success on each trial, and then it's going to return the this statement, this formula here, or the outcome, given the values we input here, it's going to return a probability using this formula, which is the binomial PMF formula. But this time, rather than having to create our own function to work out the binomial coefficient, we're using the one that already exists in the math library. So math.comb, and it takes comb or comb, the combinatorial method. It takes two arguments, n and x. So n being number of trials, x being number of successes, and then that's multiplied by p to the raised to the x power. So double asterisk here is an exponent, a single asterisk is a multiplication, and then that is multiplied by 1 minus p, which is raised to the n minus x power. So hopefully it's clear. N, number of trials, x, number of successes that have been observed, and p is the probability of success on each trial. So if we run that, we've created our function for that gives us returns. We give it certain values, certain arguments. It'll tell us probabilities using the binomial distribution. So let's kind of, same as we did in the previous video. Let's say we have data from 10 trials. We observe 4 successes, and we know the probability of success on each trial was about 30%, 0.3. So what that's telling us is we've got from the probability of getting 4 successes from 10 trials when p is 0.3 is about 0.20 or 20%. Okay, so much simpler way there for us to obtain the binomial PMF, but remember we have still had to define our own function. In the next video we'll take a much easier route to doing this. So the next thing, we've got our binomial PMF. We can use this function as part of a larger function. We can nest it within a function to obtain the binomial cumulative distribution function. So I can't remember in previous videos if I've referred to this, the CDF, the cumulative distribution function, as the cumulative density function. I think it's actually the cumulative distribution function. I often confuse the two. But to obtain the binomial CDF, we need to sum over all values of the PMF, the probability mass function. And to do this, we need to make use of a floor operator. So that is a mathematical operation that rounds positive decimals down to the nearest integer value and negative decimals down to the nearest integer value away from 0. Okay, and the math library, making our life much easier here, has a floor function that we can make use of to do this. So this is math.floor. So here, what I'm doing in this cell is defining a function for the binomial CDF, cumulative distribution function, making use of the floor method contained within the math library. So I'm defining a function. So there's a def reserve word called binom_CDF. It takes nx and p as arguments, number of trials, number of successes, probability of success. I'm initializing a p-value at 0, this object called p-value at 0. And then I'm creating an object called x_floor, so a floor operation on the x value we give. And to obtain that, rather than having to kind of create our own recursive way to do this, I'm just using the math.floor method and passing x to it. And then a for loop for I in range x floor plus 1, p-value is equal to the p-value plus whatever arguments we've put in our binomial, whatever arguments go in here that fit the binomial PMF. Okay, and it's going to return a p-value essentially. Let's run this code. But it's similar to what I did in the previous video. It's just it's been made simpler by the fact that we've some of the things you need in order to obtain the binomial coefficient, and in order to obtain the binomial PMF, and in order to conduct a floor operation, are being done for us by software. Okay, so let's run that again now. What we should see here is we're gonna kind of input some arbitrary values into the CDF function we've just created. We're going to say from 10 trials, and we've observed 4 successes with a probability of 0.3. What's the probability of observing 4 successes or fewer? Okay, that's what the cumulative distribution function gives us. And you can see there, if we round that up, it's about 85%. So the CDF for the binomial gives us the probability of getting X or fewer successes from 10 trials, from N trials in this case. The probability of getting 4 or fewer successes from 10 trials, with a success probability on each trial of 0.3, was about 0.85 or 85%. So these were the kind of same values to test these functions as I used in the previous video, and you can see we're getting the same results. So that is that using these existing kind of methods from the math library has made life a lot easier when trying to kind of work out probabilities for a random variable that follows a binomial distribution. In the next video, we will use SciPy to do a lot of this stuff, and you'll kind of see that makes life a lot easier. So you wouldn't really need to go through all the kind of all the work and effort that was required to calculate this manually, or to create your own functions to obtain these values. Okay, so that's a little bit more on the binomial distribution. More to come in the next video. We'll do the same sort of thing but using the SciPy library, and then we'll kind of look at how to simulate data that follows a binomial distribution. I hope this was useful, and thank you for listening.